Okay, lines there, the field measurements. We have very few measurements close to the ground, but these full-scale measurements are necessary. We need them to validate some of these experimental and computational simulations that are out there. And as Greg mentioned, ASC 722 is likely going to have a tornado loading chapter, and we need an atmospheric boundary layer analog to include tornadoes in codes and standards. And so what I'll talk about is a lot of the work that we're doing at Illinois, and really the methods and techniques that allow us to capture some of this elusive full-scale information on tornadoes. And so Greg mentioned the work we're doing to estimate the wind field. And so, for example, this shows tree fall patterns on the left. These patterns are digitized, and then vortex models are run. And on the right there, you can see in the black arrows, a simulated tree fall. We compare that to the observed tree fall and come up with wind speed estimates. And I live in Illinois, so it's a highly agricultural area. And we've noticed too that very similar patterns occur in corn, for example. So here's a picture one of my students took in Illinois in July, showing very interesting cornfall patterns, including multiple vortices. And so we can do a lot with these wind speed estimates. One is just to generate a wind field or a peak wind field. And once we do that, we can then compare to existing wind speed estimation techniques. So the figure in the bottom left, for example, is from a number of methods from a particular tornado in Illinois. The blue line is kind of a horizontal slice of the wind field based on tree fall. And you can compare that, for example, to the colored squares, which would be wind speed estimates from the EF scale. So it can be a very valuable tool to estimate not only in tornado intensity, but also tornado occurrence. In addition to estimating the wind field, some of the work that we do, we also want to measure the wind and pressure field. So the goals are really, we want to be safe, and so we want to pepper the area with low-cost sensors wherever the event is to increase the chances of an actual hit. We're developing a lot of deployable sensors. I mentioned one here. So these rapidly deployable high-resolution barometric pressure sensors. On the bottom left, you can see this is in Hurricane Laura in the US, so we also take it in hurricanes as well, showing the passage of the eye over this particular sensor. And using information on the aerodynamics of circular cylinders, for example, distribution poles, we can also use these same sensors to estimate the wind speeds. And so the example on the bottom right here shows comparisons. The red is from one of these barometric pressure sensors, wind speed estimates, compared with a traditional tower anemometer estimate. And so not only just measuring kind of the wind speed or barometric pressure characteristics, we also want to measure wind loading. And we've created a portable wind loading cube that we call MSWRF cubed to measure wind loading in these events. And so we've done some testing, and it compares very well to full-scale cubes like SILSO and cubes tested in the wind tunnel. And we obviously would like to get this in a tornado, but we're going to start in the spring looking at dust devils. They have very similar near-surface vortex characteristics of tornadoes, and we think we can get a better chance to actually capture full-scale loading using dust devils, for example. And so, in addition, we're also doing some complementary methods and techniques to some of the full-scale work with colleagues in projects in NOAA. And so we're doing some, for example, some realistic LES scenarios. Here you can see a tornado coming in contact with a large obstacle that remains mostly intact. So you can think of it as like a large building that doesn't get damaged. And you see a couple things. You see these kind of wind speed streaks here on the bottom left. And then you see this really intense speed up, large speed up in the wake of this particular structure. And so we've been looking at observed events. This is a tornado in Oklahoma, and you can see very similar features. This was a large obstacle, a large building here, very similar features with the streaks. And then again, significant damage downstream of this building. And so just to close, an application to codes and standards, I showed these tornado profiles in the very first slide. We have used this information. I was on the Tornado Task Committee for ASC 722, and we developed a proposed wind profile here for tornadoes shown in red and compared to a traditional kind of boundary layer profile that's in ASC 716 currently. So we're doing a lot of work that kind of, that's really the spectrum of tornado research right now. And that's it. Thanks to everybody, my students especially, for making this work happen.
Thank you, Frank. If I could ask you to unshare your screen, please. I made a note in the in chat that we'll take all the questions together at the end. So the second presenter that we have now is Professor Mark Sterling. Mark is the Beale Professor of Civil Engineering and Deputy Pro-Vice Chancellor at the University of Birmingham, with over 20 years research experience in wind engineering. His research focuses on transient winds, particularly the effect of extreme winds on infrastructure, vehicles and biological systems. He's a member of the BSI Wind Loading Committee, responsible for updating the Eurocode, and a member of an ASCII committee for rewriting the Wind Tunnel Standard Code of Practice, both of which translate his research into practice. So could I ask Professor Sterling, please, to share screen and give his presentation too?
Thank you, Chris. Can everyone see that? Chris, can I see a nod on your head if you can see that?
Yeah.
Wonderful, thank you. So today I'm going to talk about the compact debris flight in tornadic flow fields. What we normally do at Birmingham, what we've done for a long time, is we've played around with at full scale, but we also built physical models. And what you're looking at in the top right is a schematic of a physical model simulator that we built quite a few years ago. And then we decided, together with my colleague Hassan Humida, who I think is on the call, why don't we have a go at building that in a numerical approach, and we'll do some large eddy simulations. So that's what we did. We built it right down to the actual guide vanes as well. And we set a number of swirl ratios, and we went about simulating the flow field within them. And we looked at 2 swirl ratios, and that's what you're looking at here. We have 2 rows, 3 columns. The first row corresponds to a small swirl ratio of 0.3, and the second one corresponds to a larger swirl ratio of 0.69. And one of the benefits of doing numerical simulations is that you can get information across the entire flow field, whereas with experiments, you can only get it in specific places. So the column on the far right shows a distribution of vertical velocity. Again, black points represent experimental data. The whiskers shows the degree of uncertainty that we have, and it's actually quite a lot. And the red line corresponds to the simulations. So same for tangential velocity in the center, and same for the velocity contours. So in many respects, what you would expect to see, particularly on the tangential velocity distribution, almost linear within the core, and then gradually dying off. In trying to characterize that, we realized that we actually generated essentially 2 different kinds of vortex structures. One which has been classed as a vortex breakdown in the literature, where the recirculation cell doesn't quite touch the ground, and one where it does. And actually we defined our core radius slightly differently to a lot of colleagues, and we defined it essentially at the center of this recirculation region. Something I probably should point out as well, there's a few things in the table, but the one thing to notice is something we've defined the revolution time. And that's the time it takes for the vortice to essentially undertake 1 revolution. And a smaller swirl ratio results in a smaller vortex, so the faster revolution time in a sense. So a lot of people have done that before, but what we were really interested in is what happens when we put debris within the actual flow. So we picked 3 different sizes of debris, same density. So essentially we went from a light one, which was debris A, to a heavy one, which was debris C. As we all know, the Takakawa number is the important aerodynamic, or one of the important aerodynamic parameters, which is the ratio of the aerodynamic forces to the weight. So 3 different Takakawa numbers, and we set about, and we released 450 particles at each point in the center of the tornadic flow field to the core, and then further out as you move towards the vortex wall. And what did we see? Well, actually, you can see on one hand, our results weren't that surprising. If you have a lighter particle, it tends to travel further and for more time. So the figure, the 3 columns on the right-hand side shows the particle paths, vertical height normalized on the vertical axis, and a slice in the Cartesian coordinates on the x-axis. And you can see we have an awful lot of debris paths which essentially travel up, move around, and then come back down when it's a light debris. And when it's slightly heavier, we see they tend to get ejected further. If we look at that in terms of the actual, rather than x, if we turn it to r, just go to the next slide, you can see that in a bit more detail. Here, if you're releasing from within the core, close to the core, the particles travel upwards and then get brought back down again into the core, whereas the heavier ones tend to have more of a parabolic profile and get ejected away from the center of the vortex. And that's true really irrespective of where you release the particles from. That's what we found. What did we find that was the governing parameter? And it's important to say that not every debris was lifted. We actually find that the distribution of vertical velocity was really important in getting these debris particles lifted, and then the tangential velocity kicked in terms of transporting them. So that's a very quick whistle-stop tour. We found similar results at the higher swirl ratio, but as you can imagine, there are a few differences and a few anomalies along the way. Chris, you're on mute.
Thank you for telling the chairman what to do. Very much appreciated. Thank you, Mark, indeed. Our third presenter in this first half, and thank you both for keeping nicely to time, is Grace Yan. She's Associate Professor at Missouri University of Science and Technology, Director of the Wind Hazard Mitigation Lab. She's passionate about the mitigation of hazards induced by extreme winds, such as tornadoes and hurricanes, and the achievement of community resilience. Her research includes the simulation of different wind fields numerically and experimentally, dynamic response of civil structures induced by extreme winds, and reproduction of damage scenarios induced by extreme winds using numerical simulations. So now could I ask, well, already Grace has shared, so could I ask her to begin her presentation, please? Thank you.
After working from home for 7 months, I'm so glad to have this opportunity to talk to you all. I wish you and family have been doing well during this pandemic. So with $10 billion of annual economic loss in America induced by tornadoes, finally the concept of enforcing tornado-resistant design for normal structures has been accepted. AIC has been developing the specification for tornadic loading, which will be included in the next version of AIC 722 as a new chapter. To advance the building code development, so today I'd like to talk about what flow structure of tornado we should design against. Put it another way, what flow structure of a tornado produces more unfavorable wind loading, a single vortex tornado or a multi-vortex tornado? To simulate a swirling wind flow, we apply this cylindrical computational domain with velocity inlet here and pressure outlet here. By adjusting the boundary conditions, we produce tornadoes with different flow structures. In the computational domain of a single vortex tornado, let's include a gable-roofed building and examine the wind effects on the building when tornado moves from the left to the right. To simulate this, the relative motion is established by moving the building in the opposite direction. These are the coefficients of the total forces in 3 directions when the building moves from one side of the tornado to the other side. So I assume you are very familiar with the feature of these 3 force coefficients. The results here are consistent with the research findings published by Dr. Han. Now let's put the same building in a multi-vortex tornado. In this type of tornado, each subvortex not only rotates about their own center, but also swirls with the main flow. So here you can tell the building can be attacked by different subvortices sequentially. These are the 3 force coefficients obtained in multi-vortex tornado. 0 represents a tornado center. If you look at the first groups of peaks, don't you think they look like these peaks induced by single vortex tornado? That is to say, the action of a subvortex is like the action of a single vortex tornado. However, the attacking period is much shorter. Two groups of peaks here means the building was attacked by 2 subvortices sequentially. Now, if you look at the magnitude, all the peak values imposed by the multi-vortex tornado are much greater than those imposed by a single vortex tornado, especially FZ here is about 3 times FZ here. Now let's look at the pressure coefficients on building surface. In the multi-vortex tornado, the peak positive pressure and peak negative pressure are about 4 times and 2.5 times greater. All these results show that the multi-vortex tornado produces more unfavorable wind loading. What causes this? This is because in the multi-vortex tornado, significant atmospheric drop does not occur at tornado center. Instead, it occurs at the center of each subvortex, which is very close to the location of the highest wind speed. That is to say, the worst loading scenario should be the superimposition of atmospheric pressure drop and the highest wind speed. On the contrary, in the single vortex tornado, superimposition may not be that important. If you don't believe me, let me show you the evidence. When the subvortex attacks the building, around the building, don't you see the highest wind speed and the highest negative pressure due to atmospheric pressure drop at subvortex center? Yes, you do. In summary, a multi-vortex tornado is more destructive than the single vortex tornado. I wish you've convinced the design should be based on a multi-vortex tornado. It is necessary to consider the superimposition of high wind speed and atmospheric pressure drop at subvortex center. Should both effects be reflected on the design wind speed? Currently, we are exploring the answer to it. So it looks like we are not far away from a tornado-resistant design. However, we are still on our way to make tornadic wind loading specifications more reliable. So let's work together to address all the research needs as Dr. Cobb proposed I presented today. Thank you very much.
Thank you very much indeed, Grace, for that. And now I will hand over to my colleague, Professor Sterling, to chair the next 3 papers.
Thank you very much, Chris. I'd like to now introduce Shuyuan Cao. Shuyuan is Professor at the Civil Engineering College of Tongji University and also Professor at the State Key Laboratory for Disaster Reduction in Civil Engineering in China. Before he joined Tongji, he was an Associate Professor at the Wind Engineering Center of Tokyo Polytechnic and also an Assistant Professor at Tokyo Institute of Technology. Shuyuan works both in structural and environmental wind engineering fields. His research interests include the development of numerical and physical modeling techniques for wind engineering problems.
Oh.
Shuyuan, over to you.
I cannot share. My share was stopped.
Chris, do you have control over that again? Could you? Well, we've done well so far getting this far without a technical issue. Shuyuan, perhaps if you unshare your screen, then start sharing it again, and we'll see if that helps.
Okay. No,
Nope.
it was stopped.
Yeah, I'm only seeing a blank screen here, I'm afraid.
Sorry. No, it was stopped.
It stopped. Okay, that's rather unfortunate. This is where
Yeah.
I think we throw the call open to anyone on it who might be able to offer some technical expertise as to why this may have happened. If you have an idea, please raise your hand.
Yeah. Yeah, no, I don't have any idea. I cannot share my screen.
So Shuyuan, do you think it's possible that you could just talk us through the main points of your presentation, recognizing that it will be difficult even though you don't have you aren't able to share your PowerPoint.
Okay, so actually in our group, we currently in China, we are historically not a tornado country, but in recent years we have two F4 tornado recorded in China. So currently there's a very increasing concern on the wind on the tornadoes. So in our group, we done a numerical and also experimental studies of tornado effect. But of course, we do numerical study is not a meteorological study. In Japan, possibly Mr. Tao had done some tornado simulation by meteorological models, but we are just our simulation, just ALE simulation, is a simulation of the simulator. So our concern, actually today I want to say we have 3 points. I have 3 points. As the first thing, I think we need to have a new, harmonized description of the SOAR ratio, because currently there's a difference of SOAR ratio if the guide band is located on the ground or the guide band is overhead guide band. So there cause some difference of the SOAR ratio. We have to calculate or to propose not a geometry defined best tornado SOAR ratio. We have to it's better to have a flow based SOAR ratio. But of course, this SOAR ratio have to be very easier to be measured in the wind tunnel test. Because currently the tornado flow is very three-dimensional. It's very difficult to calculate the flow field and then calculate the SOAR ratio. It's very difficult. So we think we can do a lot of CFD simulations to try to bridge the two definitions of SOAR ratios. I mean for the ground guide band and for another for the overhead guide band. The second thing is that we think it's necessary to consider the effect of the tornado wandering, because tornado wandering always happen in a tornado simulator when the SOAR ratio is higher. So when we in the current design procedure in the modeling especially for atmospheric boundary layer wind, we consider statistic values. But for such kind of organized structure, I think we need to propose some conditional analysis to remove the tornado wandering effect, try to make the result to be comparable with the boundary layer wind tunnel test. The final thing, the third is the final. So the final thing actually I want to propose, because we now currently have a lot of CFD models and also a lot of physical simulations already in the world. I think we have to do some benchmark tests among the simulators, just as the boundary layer wind tunnel pioneers, they compare, they do validation, they have a benchmark test at different wind tunnels, try to compare result. I think for tornado node, we have to do, it's better for us to do such kind of similar work, to do benchmark test among the different facilities. Yeah, that's why I want to say. Yeah, that's the last. Sorry.
Thank you, Xuyan. Some very pertinent and important points. And we'll try and see if we can get this. If you can send me your slides, we'll try and see if we can distribute them to the rest of the people on the call.
Okay.
At a later stage, please. Thank you. If you could unshare your screen while I introduce the next presenter, which I believe is Fred Hahn.
No, it's me. It's me.
It's you, is it?
Yeah, I'm next.
Chris, you're right. Sorry, I'd scrolled down too far.
Oh, okay, fine. Go on.
You can't trust anyone these days.
Yeah, you can't. No.
So,
we need to get the screen unshared.
Xuyan, if you could unshare your screen. Excellent. So, Chris, welcome. So just to give Chris a brief introduction, although I'm sure he doesn't need an introduction. Chris read engineering at St. Catherine's College in Cambridge and graduated with a BA in 1975 and an MA and PhD in 1978. That was followed by a research fellowship at St. Catherine's College, and then also a period of research at the aerodynamics unit of British Rail Research. And then Chris finally moved to the Department of Civil Engineering at the University of Nottingham, and joined as a lecturer, reader and professor, and then moved on and came to Birmingham in 1998. Chris held a number of appointments while in Birmingham, including, well, first of all, Professor of Environmental Fluid Mechanics, Head of Civil Engineering, and he was also the Director of Birmingham Centre for Rail Research and Education. Believe it or not, he actually retired in 2017 to take up an emeritus position, but he continues to work and undertake fundamental groundbreaking research in wind engineering. And in July 2020, he was awarded the Davenport Medal, the Senior Medal Award for the International Association of Wind Engineering. So Chris, over to you.
Thank you. I have set myself 5 minutes. I want to take up the subject that others talked about, and that's how tornadoes affect crops. The technical word for crops and trees indeed blowing over in high wind is lodging. And we've done some work on this, and the work has been recently published in a journal not many of you will have seen, the Journal of Theoretical Biology. You've seen something of this sort before. These are storm tracks that show maize or corn in US terms blown over, and we've tried to put on fall directions and wind directions. Now, these are very subjective, but you can see that we can be reasonably precise about them. And a little reflection reveals they're a bit odd because there's not much of a normal tangential component, which you perhaps expect in a tornado, which begins to suggest the radial flow component is very important near the ground level. More of that for a moment. So how can we get a handle on this? The work that I've been doing is purely theoretical because, of course, being emeritus, I don't have access to grant money or anything like that. So I've just been sitting and thinking about things. Over the years, myself and my colleagues have had a long-term research framework looking at crops blowing over in high winds. And we've looked at oats, at wheat, at oilseed rape, and most recently at maize. And crops fail by either stem lodging, breaking of the stem, or by uprooting, root lodging. And we've developed a model for this that's been quite well calibrated, a dynamic model that's based on weightless cantilevers there. And from that, and the figure on the right is for winter wheat, we can plot areas in the rainfall wind speed plane for which different sorts of lodging occur. And we can also, if we think just about stem lodging, get a fairly simple formula for the wind speed at the top of the canopy at which crop would lodge. And that formula is given there in terms of plant parameters, agronomic parameters. And we've measured these, and our most recent work has been measuring them on maize through crop measurements, actually tracing crop movement in high winds. We've been able to measure natural frequencies, and also stem strength, stem thickness, and drag area, and get some estimates of lodging wind speed. So we take that, we put it together with a new tornado model that actually allows a much higher radial velocity near the ground. And this tornado model might well be of interest to other colleagues, and it's there in the paper should you wish to use it. Obviously, I can't go into it now. But if we take these things and we put them together, we can look at how crops lodge. If we just look at the top line there, for a particular set of circumstances, the left-hand figure shows the maximum value of the tornado wind speed at any one point in the field. Y on the y-axis is the direction perpendicular to the tornado. And obviously, when that value exceeds the lodging velocity, then lodging occurs. And the second column shows the x direction at which lodging occurs. It obviously occurs first in the middle. The third direction shows the actual lodging direction relative to the direction of tornado travel, and that's plotted in vector form in the final column. And we can do this for any range of parameters, and we do get quite significant changes in fall direction, and these seem to tie together with what we measure in the field. Well, we can use that. We can then say, okay, let's do 10,000, 100,000 iterations using a Monte Carlo technique to sample the crop parameters, the wind parameters, and we can predict lodging width against tornado velocity. And we can get a cumulative lodging risk that actually allows us to make some assessment of the risk of crops blowing over, and also some idea of how lodging width varies with tornado velocity, which might be useful for the sort of work Greg and others have been talking about. Very much based on UK maize parameters rather than US corn parameters, but nonetheless possibly offering a way forward here. And again, if you want more details, I'd simply address you to that paper in the Journal of Theoretical Biology. Thank you very much indeed.
Thank you, Chris, and thank you very much for sticking to time. And now our final presenter of this session is Fred Hahn. Fred is Professor of Engineering at Calvin University in the United States. He's conducted research in wind engineering for more than 20 years, primarily experimental aerodynamics and extreme wind simulations. He received his PhD from the University of Notre Dame in 2000, has worked on wind-induced vibration of long-span bridges, vortex-induced vibrations, atmospheric boundary layer simulation, and laboratory tornado simulations. So Fred, without further ado, thank you very much for joining us, and over to you.
Thank you very much, Mark. The specific thing that I'd like to talk about today is the translation speed effects on only one thing, just on the static pressure distribution of a tornado vortex. So basically the main question is this: does the translation speed of a tornado vortex change the static pressure field around it? This is a typical roof pressure signal as a tornado vortex passes. This is from some work at Iowa State. You can see the pressure signal there, and the gray line right there is the static pressure that the tornado vortex is creating, and you can see that it's a fairly sizable proportion of the overall pressure signal. If we try to subtract out that static pressure from the pressure signal, we get something different. And a lot of ideas lately with what people have been doing has been assuming that something like that is possible, subtracting out the static pressure distribution. But my question is, how well do we know exactly what that static pressure field should actually be? If we try to do field measurements to find out what those are, there's some great work that Frank was just talking about. I think some more data will be coming, but they're not easy. It's not easy to get this, especially given the scale of tornadoes and how difficult it is to get things in the way of them. Tim Samaras did some work like this. Field data from Tim and lab data from Iowa State match reasonably well, but basically this is just matching the shape and not the magnitude of these pressures. If we look at the static pressure profiles in the tornado simulator, the profiles themselves depend on swirl ratio. A low swirl ratio gives you this more narrow profile. This high swirl ratio spreads that out significantly more. The symbols that you see on here are basically peak pressures that are occurring as the tornado translates by. Surface roughness doesn't seem to change the static pressure profile a whole heck of a lot. A smooth surface is shown here in black, and a rough surface is shown in blue. Once again, those symbols there are the unsteady peaks that occur. But more specifically now today, I just want to perhaps call your attention to something different than that, and that is an unsteady effect. And specifically, what I'm talking about is basically this unsteady term in the Bernoulli equation that often is just ignored in this type of modeling. So to explore this idea, I just made a simple potential flow model of a translating vortex. I've got a vortex here that's just translating in the negative x direction like this. The unsteady potential function can be written like you see there, and you notice I've got I've got a time dependence in there. It can be shown, if we've got that kind of a model, that the static pressure coefficient is going to have an unsteady term in it. All right, this unsteady term that's got that that time derivative of the potential of the unsteady potential. So basically, if I just plot that term, I get something like this. The unsteady term is going to be 0 on the translation axis. This would be the translation axis, but it's has opposite signs on both sides. So if I'm kind of on the fast side of this, I get a larger pressure drop. If I'm on the slow side of the vortex, I get a lower pressure drop. So basically, what that means is that if a tornado is translating along this way, something like this, structures that are on one side or the other are going to have different static pressures, and it's not just that kind of main dip that we typically expect for a slow moving or a stationary vortex. So basically, to get at estimates of magnitudes here, if my translation speed is only 10% of the maximum tangential velocity, the unsteady adjustment to the static CP is plus or minus 20%. So the black line right there is basically what would happen, or what you would assume if you just ignore this unsteady effect. But the red and the two red lines there are basically 20% different, only from a translation speed of 10%. If that translation speed goes up to 20%, then this effect becomes 40%, which is getting to be quite significant. So basically, the conclusion that I have is that the potential model here is too simplistic to make any broad generalizations, but I think this unsteady effect might be significant for the static pressure, and we really should study it further. It's difficult to do this at full scale. Most lab simulators don't translate, and the ones that do translate are quite slow. So it's going to be difficult to study this in the lab. It's possible that CFD might play a nice role here. So that's what I wanted to present. Just this concern that I think that we should consider. Thank you.